How do you terraform a planet that has almost no air, no breathable oxygen, and an atmosphere thinner than the vacuum chambers where SpaceX fires its engines? You don't start with cities, and you don't start with people. You start with industry. Today, we're breaking down how Starship's oxygen plant could become the very first real step toward changing Mars's atmosphere forever. This isn't science fiction, and it's not a movie concept. This is hardware SpaceX is actively planning for right now. And by the end of this video, you'll understand why oxygen production on Mars isn't just about survival. It's about slowly reshaping an entire planet. Mars looks deceptively familiar from orbit. It has a 24.6-hour day, tilted seasons, polar ice caps, and landscapes that resemble deserts and canyons on Earth. But that familiarity disappears instantly when you look at the atmosphere. Mars's average surface pressure is only about 0.088 psi, compared to Earth's 14.7 psi. That means the air pressure on Mars is less than 1% of what your body is adapted to. Oxygen makes up just 0.13% of that already thin atmosphere. Without a pressure suit, the water in your lungs would begin to boil, and you'd lose consciousness in seconds. This single limitation defines why Mars is currently uninhabitable. Here's the uncomfortable reality most people don't like hearing. Mars cannot be terraformed quickly, not in decades, not in a human lifetime, and probably not even in a century. Any claim suggesting otherwise ignores basic physics and planetary science. But that doesn't mean Mars is a lost cause. What can be done is something far more realistic and far more powerful. Mars can be slowly, deliberately, and industrially altered over long periods of time. Terraforming is not an event, it's a process, and oxygen production is the foundation that process is built on.
SpaceX's Mars architecture depends on fuel more than anything else. Starship is powered by liquid methane and liquid oxygen, and oxygen alone accounts for roughly 78% of the total propellant mass. For a fully fueled Starship sitting on the Martian surface, that means hundreds of tons of oxygen. Transporting that oxygen from Earth would be economically and logistically impossible. Every pound launched from Earth costs energy, time, and risk. So, instead, SpaceX plans to manufacture oxygen directly on Mars using local resources through a process known as in situ resource utilization, or ISRU. This is the moment Mars stops being a destination and starts becoming an industrial site. Mars's atmosphere is almost entirely carbon dioxide, about 96%. Chemically, that means oxygen is already present, just bound tightly to carbon atoms. The challenge isn't finding oxygen, it's freeing it. NASA already proved this concept works with the MOXIE experiment aboard the Perseverance rover. MOXIE used solid oxide electrolysis to split carbon dioxide molecules, producing oxygen as a byproduct. It successfully generated about 10 grams of oxygen per hour, which was a massive milestone. But 10 grams per hour is a proof of concept, not a solution. Starship requires oxygen production on a scale millions times larger. SpaceX's vision scales this idea up into full industrial infrastructure. Imagine massive air intake systems pulling in the thin Martian atmosphere. Compressors squeeze that air until it reaches pressures suitable for chemical processing. Electrolysis stacks operate continuously, using electricity to break carbon dioxide apart into oxygen and carbon monoxide. The oxygen is cooled, liquefied, and stored in insulated tanks, while carbon monoxide can either be vented or potentially reused for industrial processes. This isn't an experiment running for a few hours. It's a refinery designed to operate for years without stopping. This is where the first major payoff appears. Every oxygen molecule produced for Starship fuel also adds to the total amount of free oxygen available on Mars. At first, the contribution is microscopic compared to the size of the planet, but terraforming doesn't operate on short timelines. Over decades of continuous operation, oxygen production becomes cumulative. Terraforming isn't about instant results you can see, it's about long-term accounting. How much oxygen is produced, how much reacts with surface materials, and how much escapes into space. Mars lost most of its atmosphere billions of years ago after its magnetic field weakened. Without a strong magnetosphere, solar wind stripped away atmospheric gases over time. That process never stopped, and it's still happening today. This means any attempt to terraform Mars must constantly replace lost gases. Oxygen plants do exactly that. They don't magically fix Mars, but they slow the loss and begin to tip the balance. As long as oxygen production continues, Mars stops getting worse and starts getting slightly better. Oxygen alone doesn't make an atmosphere breathable, and in high concentrations it would actually be dangerous. On Earth, nitrogen makes up about 78% of the atmosphere and acts as a buffer gas, stabilizing pressure and reducing fire risk. Mars contains nitrogen, but only in trace amounts. This means oxygen production is only one piece of a much larger atmospheric puzzle, but it is the most critical piece. Without oxygen, there is no fuel production, no heavy industry, and no long-term human presence. This is why SpaceX's Mars plan doesn't start with domes, cities, or parks. It starts with propellant factories. The scale of oxygen production required is enormous. A single Starship launch from Mars requires roughly 1,200 tons of propellant, with around 900 tons being liquid oxygen. To support just one return launch every 26 months, oxygen plants would need to produce several tons of oxygen per day, continuously, for years. As more starships arrive on Mars, production requirements multiply. More plants, more power systems, more redundancy. At that point, oxygen production stops being mission support and becomes planetary-scale engineering. Here's a critical detail that often gets overlooked. Producing oxygen doesn't just benefit humans and rockets, it actively changes Mars's chemistry. Oxygen reacts with iron-rich Martian soil, accelerating oxidation processes. Mars is already red because of iron oxide, but increasing free oxygen speeds up surface reactions. Over long periods, this can affect how dust particles clump together, how heat is absorbed during the day, and how quickly the surface cools at night. These small changes can influence weather patterns and atmospheric circulation. Terraforming isn't flipping a switch, it's nudging a complex system again and again until the planet responds. None of this is possible without enormous amounts of energy. Solar power alone isn't reliable enough on Mars, especially during global dust storms that can block sunlight for months at a time. That's why oxygen plants will almost certainly depend on nuclear power. Compact fission reactors provide constant, predictable energy output regardless of weather or time of day. With nuclear power, oxygen production can run uninterrupted. And that continuity is essential because if production stops, Mars immediately begins losing the gases you've worked so hard to create.
This is where the long-term strategy becomes clear. Terraforming Mars isn't about turning it into Earth, it's about making it less hostile. Slightly higher atmospheric pressure provides better radiation shielding. A thicker atmosphere retains more heat, reducing extreme temperature swings between day and night. Even reaching 10% of Earth's atmospheric pressure would dramatically change surface conditions. A Mars with just 1 or 2% oxygen would significantly reduce life support requirements inside habitats, and the only realistic path to that future begins with oxygen plants designed to fuel rockets. Now imagine Mars 50 years from now. Dozens of oxygen plants are scattered across the planet, each one feeding propellant depots and supporting regular Starship launches. Each plant is also quietly contributing trace amounts of oxygen to the atmosphere. Mars is still unbreathable, but surface pressure is measurably higher. Habitats don't need to be as heavily reinforced. Spacesuits become lighter and more flexible. EVA operations last longer and become safer. This isn't terraforming as a final destination, it's terraforming as a side effect of survival. Here's the second major payoff. Once oxygen production is reliable and abundant, everything accelerates. Steel production using locally sourced materials becomes feasible. Methane synthesis becomes cheaper and more efficient. Water recycling improves. Greenhouses become more stable and productive. At that point, humans are no longer visiting Mars temporarily. They are staying. That's the difference between planting flags and building a civilization. Mars will not become Earth, at least not in our lifetime, and possibly not ever. But it doesn't need to. A partially terraformed Mars is still a radically different world than the barren planet we see today, and that transformation will not begin with blue skies or oceans. It will begin with pipelines, compressors, reactors, and oxygen tanks filling silently in the Martian night. This is why Starship matters, not because it's big and not because it's stainless steel, but because it enables industrial scale on another planet. Without Starship, oxygen plants remain theoretical. With Starship, they become inevitable. Every engine test, every tank stack, and every launch is preparation for building factories that will one day reshape an entire world. If you enjoyed this deep engineering-driven spaceflight breakdown, make sure to like the video so it reaches more space enthusiasts. Subscribe to Rocketry for more in-depth coverage on Starship, Mars, and the future of space exploration. And follow us on Facebook for daily space updates and breaking SpaceX news. This isn't just about going to Mars, it's about learning how to change worlds.